Hi everybody. We just finished Fourier series. Fourier series, as you know, is oriented towards periodic functions. What about non-periodic function? So Fourier transform is a mathematical tool which transforms the signal from the time domain to frequency domain. It doesn't have to be periodic, and that's the advantage. And we use integration, so we can call it Fourier integrals. So Fourier integrals permit description of non-periodic functions. And Fourier integral formula is a formula for the, you can say, for the decomposition of a non-periodic function into harmonic components whose frequencies range over a continuous set of values. All right, and Fourier transform can exist for energy signals, power signals, and impulse rated signals. And there are many applications for Fourier transform. So the frequency domain is very important in many applications. We can say that the frequency domain obtained from the Fourier transform can be implemented in very useful ways, such as audio processing, detecting specific tones or frequencies, and even altering them to produce a new signal. Can be using compression, how representing a signal in a frequency domain can lead to more compact representation in memory. Another application, radar, detecting how a shift in frequency of reflected electromagnetic signals related to the distance traveled and speed of object. There are many, you can read about all the applications I just mentioned for you, 3 applications. Well, now how can you use the formula of integration to get Fourier transform so you can get the frequency components of any signal? Well, the formula is really simple. It said that if you want to find Fourier transform of a function of time, let's say that you have a function of time and you want to find Fourier transform, so you write the capital F, you can write as equal F capital of omega. So when you use the small letter for function, it means function of time. And when you transform it to the frequency domain, it will be capital F. That's how can you distinguish between them. All right. That will be equal the integration from minus infinity to plus infinity for the function of t multiplied by e to the power of minus j omega t delta t. That's it. All right. And this function should be integrable over the range where you're going to make the integration. Excuse me. Let's take an example. I'm going to solve 2 examples in this lecture. Example 1. Let's say that the function looks like that. That's the time axis, and that's vertical axis, the function, let's call it f of t, and it's from -2 to +2, it's equal to 1, and there will be 0 everywhere. So, well, let's take another value, not 1, let's take 3, right? So it will be equal to 3, and from -2 to 2, and 0 outside the scales. So now I want to get the Fourier transform of f of t. So you write that Fourier transform means f capital of omega is equal. The integration should be from minus infinity to infinity of the function. But again, the function is defined only over from -2 to +2. So what you'll do, you change the limit of integration from minus infinity to -2 to +2, and the function is equal to 3. You multiply it by e minus j omega t dt, and then you do the integration. That's a very simple one. And by the way, when you have a complex integration, I put in the handout a table of integration just to look at it and just use the formula, all right? It's not questioning you how you do the integration, use the table. So 3 is a constant, and the integration of e will be e minus j omega t divided by minus j omega, and the limit of integration from -2 to +2. All right. Let's continue. So you have 3 is a constant minus j omega. This is omega. And you substitute, well, I mean, I can get rid of the minus, you know, the same trick that we do. And we change the limit of integration, or flip them, -2 + 2, all right? So you have e, and then you have j to omega minus e minus j to omega, all right? And now you can make simplification for this one. You know from the trigonometry that sine theta is equal to e to the power of j theta minus e minus j theta divided over 2j. So this function, if you multiply both sides by 2j, what you'll get this expression, all right? So this one, this expression is similar to this one. So what you'll do, you are going to say is equal to, what is that? That's f of omega is equal 3 over j omega. And this expression will be replaced by 2j sine theta, and theta here is equal to 2 omega. J cancel j, and 2 times 3 is equal 6. So that will be equal 6 over omega times sine 2 omega. That will be the f omega. All right. So that's the expression that we got. That's the Fourier transform of the function. All right. Let me take another example. In this example, just, I mean, the graph was given of the function. What about if the function is given like a mathematical expression? That will be our second example. Example 2. The function given f of t is equal to e minus 2t ut. Find the corresponding Fourier transform of this function. Well, I want just to remind by something. Once you see any function multiplied by u of t is a step function. And the step function is start from 0 up to infinity, equal 1. So when you multiply by any function, does not change it. 1 multiplied by anything is the same thing. But ut, as you know, is equal 0 if the time is less than 0. So if this is t equals 0, that's 1 and the 0. So when we multiply this is u of t, step function. Multiplied by this function is equal e minus 2t, it will be something like that. And at t equals 0, it's equal 1. So when you multiply this function, which is e minus 2t, by the unit step, this part will be gone because multiplied by 0. So this is the only part left. That's, I mean, if you want to sketch it. So the function in our hand now can be plotted in this way. They call it f of t, not x of t, it's okay, f of t, and then start from 1 and going to 0 when you go to infinity. That's 1. So that's the function f of t, which is equal to e minus 2t ut. All right, I want to find the Fourier transform. Fourier transform, let me just write the formula. F of omega, f capital of omega is equal the integration from minus infinity to plus infinity, f of t e minus j omega t dt. Well, first of all, it starts from 0 to infinity. Beyond 0, it's equal 0. So I'm going to change now the limit of the integration, start from 0. The function is equal to e minus 2t ut. Now, since I changed the limit to start from 0, you don't have to write ut here again because already it affected the limit of integration. So I will just replace the function by e to the power of minus 2t. Now, what you will do when you find, I mean, two exponential functions multiply, you add the power of both. So you have the integration from 0 to infinity and e, and you add both. When you add both, minus 2t minus j omega t, take minus as a common factor, that's what we'll get. Take t as a common factor, so you'll have minus, 2 plus j omega, all multiplied by t delta t. Then now we'll find the integration. When you find the integration, it's very simple. It will be e minus 2 plus j omega t divided by minus 2 plus j omega, and the limit from 0 to infinity. I'm going to change, I'm getting rid of this negative sign, so I have 1 over 2 plus j omega, and what's left here, e power minus 2 plus j omega, all multiplied by t, and I'm going to change the limit because I got rid of the negative sign. Now, I will have 1 over 2 plus j omega, and I will start substitute. Put 0 here, e bar 0 is equal 1, minus e bar minus infinity is equal 0. It's done. So it's equal to 1 over 2 plus j omega. And you will find this value in a table because I give Fourier transform to most common signals in the back of the handout as a reference for you. Now, you found that. I mean, till now we feel like we are doing math and you don't understand how can you implement this. In this example, I'm going to tell you how can you use this information when you get the Fourier transform of a signal. F of omega is equal to 1 over 2 plus j omega. It's a complex. It's a complex variable here. We can have the magnitude and the angle. Well, the magnitude of the Fourier transform, it will be equal to 1 over 2 square plus omega square square root, right? That's the magnitude, all right. So when you do that, you will have 1 over square root 4 plus omega square. That's the magnitude, right? And the angle of Fourier transform will be equal, the angle of the top, 1, the angle of the 1 is equal 0 degree, and the angle of the bottom we say minus. So when you have like a rational function like that, 1 over 2 plus j omega, you will have the angle of the top minus the angle of the bottom. The angle of the top is equal 0 because it's constant 1, and the bottom will be 10 minus 1, the imaginary over the real, which will be omega divided by 2. So that will be the angle. Now we are going to sketch two graphs, one for the magnitude and one for the angle. But let's just start with the magnitude. We say that the magnitude, let me just write the magnitude m is equal to f of omega magnitude. We found is equal 1 over 4 plus omega square root. What's happening now, you have a relationship between the frequency and the magnitude of this component. So you have this expression shows the relationship between the magnitude of each component at specific frequency. So omega is changing from negative value to positive value, all right? So you can choose, for example, I mean, when you make a table, just to get a feeling of it, you can get like omega that you make, this is your omega, and this is the magnitude, and just you make your table. And you can start, you can put 0 in the middle here. And when you put 0 in the middle, let's find the magnitude. When you put omega 0 in this expression, you'll find that 1 over square root of 4, it means 1/2. So you have 1/2, 0.5. And then you go to the left, for example, -5, -10, -15, but I don't have space here. You can have it, you know, if you do MATLAB, you can take like, 10 values or 20 values, doesn't matter. So 10, 15, and you start to plug numbers. That's why MATLAB is very useful in this one. Plug the numbers of the frequency omega into the expression and find the magnitude. Well, for example, when you plug -5 will be -5 squared, excuse me, will be 5 is be 25 plus 4, 29, square root of 29, 1 over, and you continue to calculate this value, and you observe when you put omega equal minus 5 or omega 5, you'll find they are the same. So when you put a value negative and positive will be symmetric about. And then I did that, and I found that when I sketch the relationship between the speed and the magnitude of the frequency component, I have in the middle 0, I have 0.5, and then I found that is like, getting lower every time you increase the frequency. So it tells you that this function, the exponential function, has many frequency components, many harmonics, and it has a DC at the frequency equals 0. It means DC components equal half, and you can find the value or at each frequency, the magnitude. Just you look at the curve and see how much do you have, what is the value, what is the amplitude. And if you're designing a system and you want to get rid of some component, you can design it the right way, all right? Or if you make an analysis of a system, you can know what is the effect of each one on your system, because you know its magnitude. And also you can do the same thing for the phase. So you make, the same table. Actually, I usually do in the same table, I write here phase. I call it phi. All right. Phi, it's the phase. Let me just write here to know what this is, the phase, and this is the magnitude. And then try to put omega equals 0, for example here. When you put omega equals 0, 10 minus 1, 0. So what the angle? It's 10 is equal 0. 10, you remember, is equal sine over cosine. So it means the angle at sine is equal 0, which is 0. So 0 minus 0 is 0. So it means it's a 0 degree. And then you go till infinity and minus infinity. So you ask yourself when it's going to equal to infinity. When the cosine, because 10 is equal sine, 10 is equal sine over cosine. So that will be equal to infinity when the cosine is equal 0, right? Cosine, I'm sorry, when cosine is equal 90. So at 90 degree, it gets infinity and minus infinity. So when you sketch the phase, that's the omega, and that's the phase. It's equal 0 when omega equals 0, but when omega is getting toward this one, would be going to minus 90, and when it's going up here, will be going to closer to plus 90, big infinity. Remember, you have here, 0 minus the angle, so 0 minus 90 be minus 90. That's why when I'm getting the omega and the positive side is getting minus 90. That's why. So now we have the plot for the magnitude and the angle of each component for each harmonic that we can help you design system. That's one method how to find Fourier transform. And there is another method we're going to explain in the next lecture.